And if you are curious to know how the scientists are studying the reaction mechanism, let us briefly look at how it is actually being done. So, in the case of elimination of alkyl bromide, this produces basically a bromide ion. So, when Rx is eliminated, this gives an alkene and H plus and X minus. So, these are all the product which are formed in this reaction. So, the H plus is basically added to the base which is used, and the X minus is formed. That means the alkyl halide anion is formed. So, that means we can measure the formation of this halide anion, that actually tells like how the actually reaction proceeds. So, people studied the formation of the bromide ion. So, they used the Volhard method of titration. So, silver nitrate of known amount in excess was back titrated with sodium thiocyanate and ferric ammonium sulphate as the indicator. That exactly tells how much of the bromide ion is formed in that reaction. So, from that they can actually back calculate and tell how the reaction actually proceeds. And also the formation of the alkene, because we only looked at the formation of the bromide ion, which is the byproduct. This is not the main product. So, this is only the byproduct in the reaction, but alkene is also formed in the reaction. So, how do we know how much of the alkene is formed? So, that can be estimated using bromination in chloroform. So, the obtained alkene is actually treated with the bromine, followed by treatment with potassium iodide. So, this liberates potassium iodide in the presence of HCl. So, the liberated iodine was estimated using standard sodium thiosulphate titration. So, this way also we can exactly find out how much alkene is also formed in the reaction. And of course, people also carry out deuterium analysis by combustion of the compounds and purification of the resulting water. That also gives indication, because the H plus is formed in this reaction, right. So, this H plus, if they use deuterium, then we can also study how much deuterium is actually present. So, by using the deuterium analysis also, we can calculate or find out how the reaction actually proceeds. So, we can study based on alkene, we can study based on the bromide ion, we can also study based on the hydrogen or the proton which is liberated in that reaction. So, by using different methods, people study the reaction mechanism. And Sir C.K. Ingold, Hughes, Hauser, Scheiner and Saunders are various important scientists who studied these reaction mechanisms elaborately, especially Saunders worked on kinetic isotope effect of all these reactions. So, because of their contribution, we now know what is the mechanism and how the reaction actually proceeds. So, how do we know this is an anti-elimination? If you look at the historical evidence, we have chlorofumaric acid and chloromaleic acid are two isomers. So, when the trans isomer is actually subjected to elimination, this undergoes fast elimination to give the particular alkyne, that is in the presence of KOH. The hydrogen and the halide are in the trans or the anti orientation. So, this gives the reaction very fast to give the alkyne, whereas when the hydrogen and the chlorine are in the cis orientation, this reaction was very slow. So, this is one of the evidence people suggested that this kind of elimination actually occurs via the anti arrangements. And of course, there are also other examples like the meso derivative, the meso dibromide as shown here. When it undergoes elimination, this gives the cis product. So, that means the phenyl group, both the phenyl groups are on the same side. So, this here, this phenyl and this phenyl are on the same side. So, you can actually see here these are on the same side. This is the Newman projection of the same molecule. The meso compound is shown here, and the bromine, when the elimination happens, this bromine and this hydrogen, these are actually in the anti orientation. So, when that is eliminated, we end up with this cis olefin. And when we have a DL pair, what happens is, if you write the Newman projection, here if you look at the same thing, this bromine and this bromine are actually anti. So, that means we have to rotate the molecule in such a way that one of the hydrogen comes to the anti orientation, and when that happens actually the phenyl groups are in the opposite or in the trans orientation. So, that means we end up with the trans product. So, this is also another historical evidence which shows that this E2 elimination actually proceeds via anti-periplanarity is the stereochemistry for this particular elimination. Let us look at some historical fact. Basically, when people studied the elimination reaction, actually elimination and substitution both were occurring simultaneously. So, people when they studied both the elimination and the substitution reaction simultaneously, and Lebel in 1911 and Lewis in 1923 proposed a single step mechanism or a single step process, which is the E2 mechanism basically, or SN2 mechanism we can say. So, what they have studied was introduction of the entering group and the expulsion of the leaving group are a simultaneous process. That means the hydrogen and the leaving group are actually involved in the rate determining step. So, why they used the word entering group? Because they studied about the nucleophilic substitution reaction, because nucleophilic substitution and elimination are competing reactions. We will look at how they compete each other in the later part of the series. Now, at least you can remember that substitution and elimination occur simultaneously. So, in the case of substitution we talk about entering group, in the case of elimination we talk about the hydrogen which is being removed. So, they used the substitution and elimination simultaneously for their reaction mechanism studies. So, in 1925 Lowry proposed a two-step process. So, here the initial ionization to form a positively charged ion which then combined with the nucleophilic reagent. So, this again is based on the nucleophilic substitution reaction, and Ingold in 1927 suggested that both type of mechanisms are possible, because Lebel and Lewis suggested single step mechanism, Lowry proposed a two step mechanism. In other words, the first one is a SN2 type mechanism, the second one is a SN1 type mechanism, but in 1927 Ingold suggested that both are possible. It is neither SN2 or SN1, but both reactions are possible. That is what Ingold had suggested. The main thing what all the scientists had observed was the Arrhenius energy of activation, or the energy of activation is higher for the elimination compared to the substitution. In other words, high temperature favored elimination. So, this is the study they have actually identified. So, based on these facts, they proposed different types of mechanism for the reactions. Sir, you said the more branched alkene are more stable than the less branched one, but as we know, branching leads to congestion, whether it is in the starting material or in the final product. So, more branching would be less stable. Can you please explain why this is not the case? See, here we are dealing with only alkyl substitutions. So, alkyl groups are plus I effect groups. So, more alkyl groups on olefinic carbon leads to more hyperconjugated stabilization in the transition state. So, this is the most important thing. We are not dealing with the final product, but we are dealing with the reaction itself. So, in the reaction, transition state is very crucial for the product formation. So, more hyperconjugation is favoring the more branched product. When we say stability, we can only consider the area available for the electron to move. That means, according to MO theory, we have a delocalized electron movement for the bonding. That means, more area means less electron repulsion. And of course, stability is simply a measure of the energy, and the stability is basically calculated by the analysis of heat of hydrogenation. So, here there is a heat of hydrogenation for various alkenes are given here. So, the energy that means enthalpy of hydrogenation is given here, and if we take the unsubstituted or the ethylene molecule, the energy of hydrogenation is very high at minus 32.5, whereas in the case of tetra substituted one, it is much lower. In other words, this is much more stable compared to the ethylene molecule. And of course, we can also see the gradual change. When there is a mono substitution, the energy drops a little bit, but when there is a cis disubstitution, that energy still drops. But between geminal and the trans orientation, as we know, cis isomers are a little less stable compared to trans isomer, we already know. So, that can be explained here based on the enthalpy of hydrogenation of that particular alkene. And when we go to the tri, we have a much higher stabilization, and when we go to the tetra, that is having the maximum stabilization. So, this is how we can say how the energy of enthalpy of hydrogen can be used to explain the stability of different alkenes.